We will continue from last week. So remember the last Thursday we had a discussion session, right? And we were looking at DTFT, discrete-time Fourier transform. And so in that discussion session for homework number 1, you got a chance to deal with both the forward and the forward transform and the inverse transform. Forward transform from time to frequency, inverse is from frequency back to time. Okay, so this is a version, 一种版本, a Fourier transform that was defined on discrete time sequences. So today we are going to continue, and just to in case that you have already learned DTFT before, most likely from signals and systems, this will be a review. But for those of you that are, some of you this might be new, but selected properties. So here I say selected property, 用选择性的啊。So we are not going to my intention 我的目标啊。My intention is not to cover everything there in DTFT, but instead I choose to focus on just a few properties that I found most useful for the rest of the semester. So there will be a discussion on selected properties of the transform. With that, let me first, let's just look at the definition again. So for any time domain signal x of n, being a sequence of number, n, let me emphasize one more time, n is an integer. Okay? N is a time index, and by default is an integer. So xn, we multiply it with e to the minus j omega n. Here the variable small omega is the frequency, which I recommend is, we use it around the unit circle. So let's say from 0 to 2 pi, or if you will, from minus pi to pi, because it's gonna, later you will learn that it is periodic, okay? So doesn't matter, omega is any interval, any closed interval 2 pi, from minus pi to pi, or from 0 to 2 pi. So omega is the frequency. So last time I spent a few moments to share with you that there is a conversion between small omega and big omega. I need to know that small omega has it doesn't have a unit. Or if you really want, then the unit, I would say the unit of small omega is radian per sample, which means how much of a phase change is introduced by going forward in time from going from n to n plus 1. If you move in a time domain by one sample, how much phase change is there? That's the meaning of small omega. Okay? But whereas big omega really has a unit of radian per sample, per second, radian per second. So which equals to 2 pi times hertz. 2 pi times frequency in hertz is the big omega. Okay, so just to summarize, so here's my recommendation. Just please learn to, you'll get used to this. Okay, whenever we sample a signal, so it becomes a sequence. Now time index becomes 1, 2, 3, 4, 5. Right. So now the relation between small omega and big omega really is a factor of t. So they are, of course, proportional, right? So last time we spent a few moments to talk about this particular example where we define the sampling rate. If the sampling rate is given to you, it's 48 kilohertz, then when we look at this frequency small omega, if it's pi divided by 6 or 30 degrees, 30度, pi divided by 6, pi over 6, and you will just learn quickly that it should correspond to 4 kilohertz. 4 kilohertz. And the way I remember it, do you remember how I remember it? So I said that almost I just automatically, whenever I see small omega, I think of pi as the Nyquist rate, because pi is 1/2 of 2 pi, and 2 pi corresponds to the sampling rate. Right? So pi corresponds to Nyquist rate, which is half of that, equals to 24. Therefore, you can calculate quickly any given frequency small omega we can calculate quickly how that corresponds to a frequency back in hertz in the time in continuous time. Okay? So there's a simple relation over there you should be aware of. 你需要知道 you should be aware of. Any questions so far? That's from last time. And the inverse transform is something that we introduced right away last time. Okay, when we have the Fourier transform, we have the inverse transform. You can easily check that indeed, if we are given the definition of big X, a spectrum. So what we do here in this definition, we take the spectrum and multiply it by e to the j omega n, because the spectrum tells us how much of the signal is there at this particular frequency, right? And one particular frequency, so this is a complex valued coefficient, and then we multiply it with ej omega n, which can be regarded as a small wave, and then we accumulate all the frequency over small omega, and there should be a normalization factor. You don't want to forget that. And you can easily check mathematically that indeed, when we just do this calculation, it gives us back, this is what we get. We get back the signal in time, okay, by starting with the spectrum. So this is an inverse transform, which goes from frequency domain to time domain. Okay, inverse transform, and we have checked that. So today, in the next few slides, I would like to talk about my selected properties. And you can find these properties on the textbook for sure. In the textbook, you just check these two sections, okay? Check those sections and you'll find a more complete coverage of all the properties that are known for discrete-time Fourier transform. But first one, I'd like to mention that our spectrum, when we talk about DTFT, the spectrum is going to be periodic. Periodicity, 周期性, it's going to be periodic. And so that's an easy property. And you can just, by looking at the definition, you should notice that. So I want to just summarize that the first property you should be aware of is periodicity. The 2 pi, any spectrum for DTFT. This will not be true for general Fourier transform, not true. But for discrete time Fourier transform, when we use small omega to denote the frequency, this spectrum is periodic. Every 2 pi, the spectrum repeats itself. Okay, some of you also pointed out last Thursday when we met for discussion. Yeah, of course, they are periodic. So that being said, I often told my graduate student, okay, when you plot DTFT, there's no need to repeat, okay? If I asked you to make a sketch for your homework or for your tests, if I ever ask you to sketch a magnitude spectrum for any DTFT, please, you can just plot from 0 to 2 pi, something, okay? Or you can plot from minus pi to pi. And that'll be great, okay? Yeah, for the same thing, actually, sort of the same thing. There's no need to repeatedly plot beyond a period of 2 pi, because the spectrum itself is guaranteed to be periodic, okay? There's no exception. There's no exception, okay? So let's say if I ever asked you to plot the magnitude spectrum of a signal, then just plot it with an interval of 2 pi. That will suffice, not just go, that will suffice. Periodicity. Can we move on to the second property? Okay, the second property is also quite important. So I recommended to you that in this classroom, in this entire semester, unless we mention otherwise, so if we don't mention, then we assume that our signals in time is real valued. Real valued. 它的值是实数的 real valued. Unless we mention otherwise. unless we emphasize, oh, well, this time xn is complex number. Okay. Otherwise, if xn is real to begin with for all n, then we have this symmetry property, number 1. Number 2 and number 3 are both symmetry properties, 是对称性的, about symmetry. The first thing, number 2, if time domain is real, then what we have here is that when we evaluate the spectrum at minus omega, that's where I read it. If we evaluate, 去计算, 去评估, if we evaluate the spectrum at minus omega, then the result is going to be the spectrum at plus omega but conjugated if the signal is real to begin with in the time domain. Okay? And we can easily check that. Okay, let's check this. Number 2, is it really the case? Number 2, check. So easy enough, we are going to evaluate our spectrum in the negative omega, at negative omega. So by definition, we apply the, the definition is, sure, we have xn e to the minus j, but minus omega n, and we sum over all n, and where we assume xn is real to begin with. So that's the meaning of evaluate the spectrum at minus omega according to the definition, right? And what's next? Apparently, minus and minus, we have a plus, right? So next step, of course, this is xn e to the j omega n. And this is, of course, summation n, x of n, e to the minus j omega n conjugate. And here we do take we take the assumption that xn is real, that x, the signal, is real. Then just conjugating the sum equals to the sum of conjugating individual terms. That's right there. So that's, then here we finish the check. Okay. Indeed, when we evaluate the spectrum at negative frequency, then it's going to be the same as if we are evaluating it in the positive frequency but conjugated. Okay, so that's the symmetry. When we replace omega with minus omega, then the result is complex conjugate. Okay. 共二复数啊，叫 conjugate 这个字啊 ，conjugate. Let me just write it. Conjugate. That's in Chinese is 共二复数啊 conjugated. Yeah. Okay. So what's the implication? What's the implication property number 2? If I ask you to plot the magnitude spectrum again, for a signal that you know is real, then what's the consequence? 后果是什么? What's the consequence? Do you really need to plot from 0 to 2 pi? The answer is no. Or this should be clearer. Do we need to plot from minus pi to pi? The answer is no. Why? Because of the left and right, the magnitude spectrum will always be evenly symmetric. Yeah? When you flip the spectrum left to right, it's always the magnitude spectrum, I mean. Yeah. The magnitude spectrum. So there's a kind of a consequence. Let me write it. Okay? Because of number 2, so therefore, x e j minus omega, when you evaluate the magnitude spectrum at negative frequency, negative omega, it's going to be the same as evaluating this, right? What's here is equal to what's here, right? I will just taking the magnitude, taking the absolute value. But then, what's the absolute value of a complex conjugate of any complex number. It's the same, right? It's the same. The absolute value of a complex conjugate to any complex number is the same, right? Remains the same. Therefore, we have this so we obtain the result. When we evaluate the magnitude of a spectrum at minus omega, the result is going to be the same as the magnitude spectrum at plus omega. In other words, the magnitude spectrum, when we take the absolute value with the magnitude spectrum, it's going to be evenly symmetric. It's going to be evenly symmetric. So therefore, if somebody just plot this, let me just erase. If you just give me this plot, I give you full credit, okay? 这也是满分的啊。As long as our signal is real in the time domain. As long as our signal is real in time domain, which most likely will be the case. Right? So that's sort of a kind of a practical consequence of this nice property. So this symmetric, so you don't need to plot the negative part because it's always going to be symmetric. Okay, I'm not doing a very good job, but you know what I mean. All right, so that's property number 2, symmetry in the frequency domain. But how about now symmetry in the time domain? We know that in Fourier transform, a lot of times we have a property in the time domain, we have the equivalent property in the frequency domain. And you can call it duality, 对偶性，有这种的 duality. So if we have a symmetry property in the frequency domain, how about in the time domain? If we assume that our signal is real and the signal itself is evenly symmetric in the time domain. So given these two conditions, it turns out that you can show that the spectrum is going to be real valued. In other words, there will not be the imaginary part. The imaginary part of that spectrum is going to be 0. Purely real. Okay. So I leave the proof as an exercise. Okay. So, but keep in mind that whenever we have a symmetry property in the frequency domain, you have the corresponding property in the time domains. This is one example of duality. The duality of Fourier transform. This property will be useful later on when we design filters. I can promise you, yeah, we will use it. We will use it. Yeah, kind of a nice property. And can I move on to the next property? Okay, this is the shift theorem. Okay, the shift theorem, where we have this notation. Let me introduce this slowly, okay? So here we assume that there's a signal x for sure, but n, but we define another signal y. If we define another signal y which equals to x evaluated at n minus a fixed number m, okay? So let me be clear that here m is a fixed number, n is an index. N is index 1, 2, 3, 4, 5. Okay, and m is a fixed number, a fixed integer. Could be positive, could be negative. But m is a fixed integer, right? So by this definition, hopefully we can imagine that what's the relation between y and x? Y is just x delayed by m samples. Can we agree on that? Y is just m delayed. 延后的 delayed by m samples. M could be 3, m could be 100, m is a fixed integer. Okay, so if y is simply x but delayed by a few samples, by m samples to be exact, then we have this relation. Then we have the relation that the spectrum of y is going to be x, but multiplied with this extra term right there, multiplied by a fixed complex number. Okay? Multiplied by that. I'm sorry, not a fixed number, but I mean m is fixed, but omega is still there. Okay, multiplied by this term, we can call the term a linear phase term. A linear phase term. Okay, so let me write this down. Let's have a brief discussion on this property. Let me, just erase this part. Shift theorem. And by the way, in tomorrow's discussion, I asked you to sign up. This is the first question for tomorrow's discussion. I'll ask any volunteer, if you will, come here to show that this is true. Okay, but here I would want to introduce, share with you kind of a physical insight. What's going on here when we shift a signal by m samples in time? It introduces a phase change for every frequency. And that phase change is e to the j omega. That phase change is omega times m. Okay? So let me point out. So yeah, if this is true, we are going to show it tomorrow in the discussion session. But here is my insight. If this is true, let's assume that this is true. Okay? Yeah. Let's just for the moment agree that this is true. And what does it tell us? Yeah. Here's my insight. We can take the phase of the spectrum. Right? We can take the phase of the spectrum. Yeah. We take the phase of the spectrum. And we know that when we multiply two complex numbers, what happens in the phase? When we multiply two complex numbers, the phase adds, right? The phase is summed. The magnitude will also multiply, but the phase is summed. So the phase add on top, right? So we get this result. We get, this is complex number, it looks like that, and plus the phase of the original, the spectrum of x, big X, okay? Yeah. So far, so good, okay? The phase will have this summation relation. But there is an interesting property called group delay. Group delay. So it's defined as partial. When we take the partial derivative of a phase spectrum with respect to frequency, this quantity, and there's a minus sign, is called group delay. I should say group delay. I mean, anyway, yeah. Let me just, for the time being, say it's group delay, okay? Yeah. So that's a definition that's that we evaluate for y. Okay? For any spectrum y, we can evaluate its first derivative of the phase with respect to omega. Okay, phase on top, omega at the bottom. Okay. So if you do that, there's a negative sign. Then we are talking about partial here, partial omega plus partial x, the phase spectrum of x, also with respect to omega. So there's a simple equation, right? If this is true, if that's true, this is true, then this should be true. The equality should hold over here. Okay? So what do we have? So what's here? What's the phase of e to the j something? It's simply the exponent, right? You need to be careful. The exponent omega m, right? So yeah, well, watch me. So so here equals to omega m. Okay, is that clear? Yeah. The phase equals to omega m. I'm sorry, there should be a minus sign. Yeah, not omega m, but minus omega m. Yeah. Minus omega m. Yeah? And then when we take the derivative of minus omega m with respect to omega, so what do we get? We get m, right? We get minus m. So we have minus m, and let me just still copy that term over here, over there. I close the bracket, the brace, and then this becomes an interesting property. Okay, so now here, minus minus, we have m, and plus what? Plus something. So that means the group delay for y, for that y in the time domain in the frequency domain, the group delay for y equals to m plus the group delay for x. Yeah. So this is for y. This is for x at every omega. Yeah. So that makes a lot of sense. Why? Because if you group delay of a signal means that how long you need to wait for the sort of the center of a signal to come. Okay. So we'll come back to here. Okay. So there's a kind of deeper insight in in the shift theorem. It makes a lot of sense. When we delay our signal in time by m samples, then in the spectrum, what will we will get this result. In the spectrum, we found that at every frequency, the group delay is going to increase by m. Why? Because we delay the signal in time by m samples. Okay? So that means every frequency component is going to come m samples later. That's the meaning of group delay as a function of frequency. Yeah. So there's no contradiction. Okay, so so everything put together, they all make sense, right? So yeah, so that much we can say talk about this shift theorem, which will be discussed tomorrow, and also we are going to now move on to the next property. Right? Next property is the convolution theorem. Okay, the convolution theorem. For anybody who needs to take a picture, maybe now it's time before I erase it. Okay, picture break. Yeah, picture break. Yeah, let me go to that side. So with that, with the very useful shift theorem, then now we can officially talk about the convolution theorem. Okay, the convolution theorem goes like this, okay? So here we are talking about two signals in time. And we want to calculate what is called convolution of the two signals. So let's denote one of the signal as x, the other as h, okay? X and h. And we use this notation, x convolve with h, and here, this is my preference, or prefer, my preference of how we denote convolution. I want to emphasize that x is a signal, h is a signal, and convolution as a result is also a signal. So this is my notation. X convolve with h, and which will be a signal. That's the meaning. Right? This is why I use this notation. You might not find it in the textbook, right? But just to emphasize that the result of convolution is a signal. Okay, is a signal. We're taking two signals, and so the definition is a summation over k, and is a sum of products. A sum of product, and for every n, we would flip one of the signals. So note that here h goes backward. If we, as far as the summation is concerned, inside this summation, x k goes forward, but h, there is a minus k, h goes backward, okay? So we flip h and shift by n, and then evaluate, we sum all the products. We sum up all the products over there. That's a definition of convolution. That's a definition of convolution. So here, as I just to sort of go through, y, this definition is called the convolution of x, signal x, and signal h. And next, I'd like to point out that please note that convolution is commutative, 具有可交换性 commutative. Doesn't matter. X convolved with h equals to h convolved with x. You can check that. Convolution is like addition, like multiplication. 就像加法跟乘法 Convolution is also commutative. 是具有交换性的 commutable. So it doesn't matter x convolved with h or h convolved with x. The two of them are equal for any arbitrary sequences x and h. All right, so now the convolution theorem goes further. What happened? The issue here is what will happen in the frequency domain. What will happen in the frequency domain? When we convolve, we take the convolution of signals in time. What happens in the frequency domain is multiplication, even simpler. Even simpler. So we convolve in time. So it turns out we will show that we can show that, and we will show that in the frequency domain, we take the product of two spectrums, and the result is the spectrum for the convolution convolution. You take convolution in the time domain, the result that the consequence is that the two spectrums will multiply in the frequency domain, right? For all omega, and this property is called the convolution theorem. Okay. And convolution theorem is gonna show up everywhere throughout the semester. When we talk about systems, when we talk about any linear time invariant systems, okay. So in this semester, we will just mostly use h to denote the impulse response of a system, where x will be our input. So just to put this thing into a bit of context, we would often talk about a linear time invariant system, which has an impulse response denoted by h. Okay, impulse response is a system. The impulse response of a system. So the context often goes this way: if h is the impulse response of a system, and then we take x as the input, then the result is going to be x convolved with h. X convolved with h. Yeah. So that's the most often the number one context in which we use the convolution. We think about the convolution theorem. Okay? We'll come back to this. Okay? We'll come back to this. Now, next, I would like to invite all of you to work with me through the proof of convolution theorem. Okay? Let's work on that. So convolution time domain, multiplication in frequency domain. How come? Yeah. Let's make a derivation, right? Shall we? Let me just stay on this side. Okay, so we want to evaluate y ej omega. And what is y ej omega? But y ej omega, the spectrum, by definition, is a DTFT of signal y in the time domain, right? So by definition, it should be equal to summation n, yn e minus j omega n. That, right? Yeah. But then what is yn? Yn is suppose that y is x convolved with h. So yn, what is yn? Yn is a summation over all k, right? Convolution. xk h n minus k. That's y in time domain by definition. Okay? And we copy this term right here. So what's next? Almost always when we see summation, double summation, what can we try? Changing the order, right? We try changing the order. So we put k outside and n inside. So anything that has nothing to do with n can be put to the outside, which is this term right here. While in the inside, now n goes inside. Summation over O goes inside. It goes inside, and then let's just write down everything that depends on n. Okay, so that which is this. Okay, so what do we notice? What did you notice? What do you notice? Here looks like what? It looks like the Fourier transform of something, right? It looks like a Fourier transform of one thing. What's that thing? The thing is h shifted by k samples, right? So here we are going to apply the shift theorem. This is the place where we can apply the shift theorem. So here, because of shift theorem, we know that this term equals to what? It equals to the spectrum of h, but with a linear phase term. With a linear phase term, as far as n is concerned, k is the fixed number. So here, e minus j k what? jk omega. Or j omega k, if you will. Okay. E to j omega k. Okay. So we can continue, right? Now we can continue. So you are probably seeing the result. We're getting close, right? Are we getting close? Yes. Now we copy everything here, still summation over all k. xk is copied right here. But here now, what do we have? We have e to the minus j omega k. And then we have one thing right here which does not depend on k. Right? That thing over there does not depend on k, and that's almost the end of derivation. Okay? I say this is gonna come to an end because why? Because what do we have here? What's here? What's showing on here? What's showing right here? Summation over k, and k is just a dummy index, right? A dummy index. So this is exactly the spectrum of x. This term equals to spectrum of x. By definition, that's the DTFT of x, evaluated at omega, where k right here, don't worry, it's a dummy variable. Okay? Yeah, so now we have, on the left-hand side, we have y, big Y. On the right-hand side, we have the product of h and x and h. So that finishes our check on a proof of a concise proof of a convolution theorem. Okay. So far so good. Yeah. Is this good? Okay. Yeah. So I think that's a nice exercise to review once in a while. Yeah. Convolution theorem. We come back to this is super useful. Okay. Convolution theorem has a lot of meaning in this context, in the context of studying systems, studying linear systems. Yeah, we'll come back to that. Okay, so next thing, this is a bit quick, but this next thing is a beautiful theorem. Okay, perhaps one of the very nicest theorems that we'll encounter in the entire semester. So I would love to share with you. We need to know that there's a thing, a theorem that's related to energy. Energy of a signal. The energy of a signal. So let's look at the result first, okay? There's an identity, 一个恒等式 identity. This is an identity which applies, which is true for any given signal. Okay, for any given signal x. Yeah, if we sum up the square of x, I mean square of the absolute value of x, sum them up in the time domain, the result will basically be equal to integrating the magnitude spectrum also squared in frequency. This is an identity. 是一个恒等式. This is an identity which will hold for any given signal. Okay. The only there is a scaling factor that cannot be abandoned. There's indeed a factor 1/2 pi, but essentially, 本质上, this tells us energy can be calculated in the time domain or in the frequency domain, and that's very nice. Okay, and the total energy of a signal. Okay, so I say energy. I mean, if we agree that this summation can be called energy. If we call this energy, and that also makes sense. The reason we call this energy, so let me make a remark right here. We sum over all n, and when we sum over x square in time, so that's is like so let's say we have a x c of t in continuous time to begin with, right? And the unit might be volt, yeah. Okay, unit might be volt. So the idea is that if we let's say we just simply think of this as if it will go through a load of resistor, which has a resistance R, right? So if this is a voltage across a resistance, then what's the total energy dissipation? 什么 R 分之 V 平方 yeah, V square. Thank you. So V square divided by R, what is that? What's the unit of this? What's the unit of this? V squared divided by R. A power, right? It's a power. So we just take the integral of that from 0 to, let's say, to forever, yeah. dt. So that's the entire power assumption, power dissipation by the resistor R, right? So there's a kind of a connotation that when we take the square of a signal, that's directly related to power, to the power that the signal is providing, right? And when we sum up power in time, or when we take an integral of power in time, which in discrete time is going to be equivalent to summing up the square. So that's why we kind of loosely just borrow the term energy. Okay, we loosely when this is 把那个名词借过来啊 so we'll borrow this terminology energy to refer to the sum of square. Okay, sum of square. But in practice, you can imagine such kind of things. Okay, sum of square in time equals to sort of the integral of square in the frequency, and there is a factor of 1/2 pi. Okay, so energy. So the kind of message right here is an implication. Energy can be calculated in the time domain or in the frequency domain. The result is going to be the same. Okay, only difference is a factor of 2 pi, not super important. Okay, which is not that important. But any comment? If you ever wonder why the professor thinks this is a beautiful theorem, in what regard? 在哪方面? In what regard is this beautiful? Beautiful, yeah? 增加是不是? 能量守恒, conservation of energy. That's a nice way to say it. Or any other? Why do you think might we think that this is beautiful? 没有标准答案啊，就是 yeah. Any other suggestion? Any other comment? Why do we think this could be beautiful? Anything that fits in one line is beautiful, right? Yeah. 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 Oh, using the. Oh, that's interesting too. Yeah, that's an interesting observation. So there might be a concern. You might be right. There might be a concern if this thing doesn't converge, then 就拉倒. then there's no such. So we need to add a constraint. If this converges, then it converges to this integral. So that's beautiful too. Any other insight that anybody would like to share? Why do you think? Why should we think? Why can we think that this is beautiful? So I think I would like to kind of refer to linear algebra. Okay? Let's refer to linear algebra. So in the language of linear algebra, we say Fourier transform, blah, 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 点点点. Fourier transform preserves the norm. 保持范数, preserve the norm. That's my point of view. Fourier transform preserves the norm. And that's a terminology in linear algebra. Let me point out that this theorem shows that Fourier transform, and in this case, a discrete-time Fourier transform. Discrete-time Fourier transform preserves the norm. Preserves the norm. What is norm? What is a norm? Norm is about taking the inner product of a vector with itself, right? Does anybody remember? For those of you that have taken linear algebra, when we take the inner product of one's vector with itself, that's defined as norm square. Okay? So just in case that you might be familiar, let's say V is a vector which belongs to a vector space big V, and just we can endow the space with, we can define inner product, which is usually denoted as a left, right, angle, and V. Yeah. When we take the inner product of a vector in any given vector space, that is a definition of norm square. Okay, norm square. So I'm just sharing with you that this is a kind of norm square. This is like we are taking the inner product of our signal with itself in the vector space of all signals. In the vector space of all signals, for which this summation converges. Yeah. So this is just long story short. This is you can appreciate it as a kind of norm square. This is the result of taking the inner product of our signal with itself. Much like any finite length vector, right? What is the inner product of the vector itself? You sum up the square of all the components, right? So this is a kind of inner product of a signal with itself. Norm square on the left-hand side. And what's on the right-hand side? The right-hand side is just to take a similar operation, but in the frequency domain. Okay. So for any, let's say for any x and y. Yeah. For any two signal, we can define x, y, the inner product as, probably the correct definition is x and y conjugate n, right? Now for a complex valued signal. For real, you don't need to worry. But similarly, in the frequency domain, we can also make a similar definition. Okay? We can make a corresponding definition. We can also define in the frequency domain when we have x and y, we can define inner product, inner frequency for spectrums. For any two given spectrums, we can define the inner product of two functions, two continuous frequency functions. Okay? You can define the inner product as integral minus pi to pi x y conjugate d omega. So inner product on the left-hand side, inner product on the right-hand side. Okay? And if you are talking about inner product of something with itself, that becomes a norm square. Norm square on the left-hand side, norm square on the right-hand side. And what's the relation right here? What's the relation? The relation right here when we look, take a look back at this, focus on this equation. Okay, so when we just take a look again at the equation, at this identity, it tells us that by going to the frequency domain, the norm square becomes is essentially preserved, 是保留的啊。The only difference is a factor of 2 pi. But otherwise, there's an identity. Okay? And I think this is beautiful. Fourier transform preserves the norm. And this property has a lot of implication. Okay? This probably has any questions so far about, this is a lot of extra materials that I'm sharing. Let's take a break. It's about time. Let's take a 下课. Let's take a 10-minute break before we come back and complete this and finish this lecture.